Alright, so today we're going over units, significant figures, and basic SI units. So let's go over some things first. So let's go over units. So I'd say these are the three most important unit conversions to know. And of course there are a lot more unit conversions, but I would also say these are just basic knowledge, but seconds to minutes to hours, and also the mass conversions like kilograms to grams. As you won't use pounds because pounds refers to weight and kilograms refers to mass in physics. And let's move on to basic SI units. So basic SI units is basically the universally used units of in physics. So basic SI units would be time, seconds for time, and then for length it would be meters, and then for mass you would have kilograms. And let's go over some significant figure rules now. So one important thing to know is that in physics, let's say whole numbers are always at least two significant figures in physics. So let's say you had something like 640, we'd say that's two significant figures. But let's say you also had something like 20. Although it would you would think that it has one significant figure, we're going to say in physics it has two significant figures because when you write out in scientific notation, you would write it out as 2.0 times 10 to the 1 power. And another thing to know is that the amount of significant figures you use will most likely always correlate to the how a scientific notation is written out. So we'll go over that out in a little bit, but so let's say we have 0.0340. The zeros that are leading up that basically show where the decimal is, they are not significant figures, as they are also leading up to the whole number. And if there's a zero, the trailing zeros after the whole numbers, if the whole numbers are past the dot, then the zeros trailing after it will be significant in this case. But if it's like, a whole number bigger than 1, like 340, in this case, this 0 would not be significant. The only two sig figs would be 34 here, and 3 and 4. So if you were to write this out in scientific notation, it would be 3.40 times 10 to the negative 2 power. So you can see we use 3 sig figs in our scientific notation, and that matches up with what we depicted here. Alright, so let's take a look at number 23. So number 23 is how many significant figures are in each of the values. So first we have 8.263 times 10 to the negative 1 power. So again, this is written in scientific notation in which we can just conclude that there's only 4 significant figures here. 8.263 are our significant figures. So in this case, there would be 4 significant figures. And now let's take a look at number, or rather letter B. So we have 0.0414. We also said that the zeros leading up to the numbers will show where the decimal is, but these are not significant figures. So our only significant figures are going to be 414, which gives us a count of 3. And now let's take a look at C. So C is 75.0. So in this case, the amount of significant figures would also be 3 because the 0 is also significant. Like a good strategy to find out how many significant figures there are in a number, write out in scientific notation. If we wrote out C in scientific notation, we would do 75.0 times 10 to the 0 power, in which we have written down 3 significant figures. We can't just write down 75 times 10 to 0 power. That wouldn't really follow by the rules of scientific notations. Now let's take a look at D. We have 0.07 times 10 to the 8th power. Again, this is written in scientific notation, so these leading zeros are not significant. So our only significant number is 7, so this would be a count of 1. Alright, so let's take a look at number 24. So number 24 is convert the following to basic SI units or a combination of basic SI units. So basic SI units is going to be seconds for time, and for length it's going to be meters, and then for mass it's going to be kilograms. So we just have to convert all of these if they're not already in basic SI units. So we have 8.0 inches. So this is a measurement of length. So we want to convert this to meters now. So we know that 2.54 centimeters is equal to 1 inch. So all we need to do is just multiply 8 by 2.54, and then we'd get the amount of centimeters in there. So 8 times 2.54 would be 20.32 centimeters. And now we need to convert it to meters. So there's 100 centimeters in 1 meter. So we just divide that by 100, in which we could just move the decimal point 2 times, in which A would give us a basic SI unit conversion of 0.2032 meters. Now let's take a look at B. So B, we have 66 feet per second. So we're working with 2 units here. We're working with some length and some time. So we need to convert, the time is already converted. It's seconds is okay. We need to convert the feet into meters. So we know that 2.54 centimeters is equal to 1 inch. And we could also just write it out like this. So we would have 65 feet per second, and we could keep the seconds the same. We just need to change the feet into meters. So we know 2.54 centimeters is 1 inch, which would mean that 1 foot is equal to 30.48 centimeters. So we would multiply it by 30.48, and the seconds would stay the same, in which there would be nothing on the bottom. So 66 times 30.48 is going to be 2011.68, and this would be our centimeters. And in order to convert this to meters, we need to divide by 100, in which we would have 20.1168, and this would be in meters per second. So for C, we have 60 miles per hour. So our 2 units is going to be miles, which is our length, and then hours, which is our time. So we need to convert miles into meters, and then time into seconds. So in order to convert miles into kilometers first, and then we'll take it to meters, we have to multiply this by, because if you remember, 1 mile is equal to 1.609 kilometers. So we gotta multiply 60 times 1.609, and then that gives us kilometers. And now to take it to meters, kilometers to meters is 1,000, because kilo. So we multiply that by 1,000. And we also have seconds on the bottom. So we have 60 miles per hour here. To change that into seconds, so first we can change that into minutes. So there's 60 minutes in hours, so we would divide that by 60. And then there's 60 seconds in a minute, so we would divide that also by 60. So 60 times 60 on the bottom. And before we do the math, we can simplify this real quick. Let's just take out the two 60s. We don't need to deal with that. And on the numerator, we're going to have 1,609 on the top, and then on the bottom we would have 60. And if we simplify it even further, we would have 26.82, and that would be our meters per second. And that is the answer in basic SI units. And one good thing to note is that I would say about 1 meters per second is equal to about 2.2 miles per hour. So it also matches up here, in which if you multiply 26.82 meters per second to by 2.2 miles per hour, by 2.2, you would get 60, or around that, close enough. But now let's take a look at D. So we have 14 inch squared. So inch squared. So we want to convert that into meters, another form of length. So we know that 2.54 centimeters is equal to 1 inch. So we want to figure out how much centimeters is equal to 1 inch squared. So we would do 2.54 times 2.54. So 1 inch squared is equal to 6.4516 centimeters squared. And the reason why we square this is because the inch is squared here. So in order to convert correctly, we would also have to square the centimeter conversions. And now what we would do is just multiply these, multiply 6.4516 by 14, because we're going from 1 inch to 14 inch squared. And we would have 90.3224 centimeters. And now we want to convert this into meters, in which we would just take the decimal and move it to the left, or divide by 100, in which our final answer would be 0.90, and that would be in meters, our basic SI unit. And meters squared, that is, so, and centimeters squared, so 0.90 meters squared. Alright, so let's take a look at number 5. So number 5, we have 75 inches. We want to convert all these to basic SI units. So we know that 22.54 or 2.54 centimeters is equal to 1 inch. So what we need to do is divide 75, or rather multiply 75 times 2.54, and that would give us 75 inches is equal to 190.5 centimeters. And now we need to change it into meters, in which we would move decimal 2 places, or divide by 100, in which 75 inches is equal to approximately 1.905 meters. And now we have B, so we have 3.45 times 10 to the 6 years, and this is a measurement of time, so we want to change it into seconds. So we have 3.45 times 10 to the 6. We're not going to multiply or simplify that out. We're going to leave it like that. So in order to change years to first, we're going to do days. We have to multiply by 365. And then after days, we have hours, which is 24. And then after that, we have minutes, which is 60. And then after that, we have seconds, which is 60. And if you do all of this math, we would get 108,799,200 times 10 to the 6th power. Now let's rewrite it as a scientific notation. So we want the decimal point to be right there for scientific notation. So how many times would we have to multiply by a factor of 10? So we could just use the little decimal rule here. So be 1, 2, 3, 4, 5, 6, 7, 8. So we would have to add 8 to 10 to the power of 6. So our final scientific notation written out would be 1.087, or rather 1.09 times 10 to the 14 power, and that would be in seconds. So it is pretty large number, and a lot of math, but that is it in basic SI units. Alright, so for C we have 62 feet per day, and we want to change the feet measurement into meters, and then we want to change a day into seconds. So to change 62 feet into meters, we would have to first convert it to centimeters. So we would do 62 times 30.48, and that would give us our centimeters, which would be 1,889.76, and that's going to be centimeters. So let's take the decimal 2 back to change it into meters. So we would have 18.8976 meters, and now we have 18.8976 meters per day. So we want to change the day into seconds. So to do that, we would divide this by day. So there's 24 hours in a day, and then we would do 60 minutes in an hour, and then 60 minutes in a second. So if we do all of that, we would get 0.0218. And if we were to write it out in scientific notation, we would have 2.2 times 10 to the negative 2 power. And that would be our time, and that would also be with the units of meters per second instead of feet per day. Alright, so with D we have 2.2 times 10 to the 4 power miles squared. So we can actually write it out. So that would be about 22,000 miles squared. So now we want to first convert it into kilometers. So we know 1 mile is equal to 1.609 kilometers, which means now in order to convert this into miles and kilometers squared, we would have to square them, in which 1 mile squared is going to equal 1.609 times 1.609, and that is 2.589 kilometers squared. So now to convert this miles into kilometers, we have to multiply it by 2.589. And if we do that, we would get 56,955.4, and that would be in kilometers squared. And now we want to change it into meters squared. So we know that 1 kilometer is equal to 1,000 miles. So 1 kilometer is equal to 1,000, or 1,000 meters actually. So in order to find 1 kilometer squared, we must square both sides now. So that means 1 kilometer squared is going to be equal to 1 million meters squared. So now we have to multiply this by 1 million to get meters squared, in which our answer would be, so our answer would actually be a very large number. So I'm going to write it straight up in scientific notation. So it would be 5.69, but we're just going to round it to 5.7. So it's going to be 5.7 times 10 to the 10th power. And that is our answer written in scientific notation. And the units to that is meters squared. Alright, so we're going to move on to 28 now, and 28 is dealing with some multiplication, addition, subtraction, division. So some things we haven't gone over yet is multiplying and dividing with sig figs and adding and subtracting between them. So these are two rules here. So when you multiply or divide with numbers and you need to get the correct numbers sig figs, when multiplying or dividing, you want to have your answer be the same sig figs as the number with the smallest number of sig figs at the start. And you'll see put it into application with these questions. So when you also add or subtract, you want to have your answer with the least numbers after a decimal point of the number with the least numbers after a decimal point. So just remember with addition and subtraction, you're dealing with numbers after a decimal point. With addition or with multiplication and division, smallest sig figs. So let's take a look at A. So we have 159.31 times 204.6. So if we multiply that out together, we're going to get 32,594.826. But we want to have the answer be the same number of sig figs at the smallest sig fig number. So in here, 159.31 has 5 sig figs, and then 204.4 has, or 204.6 has 4 sig figs. So we want our final answer to have 4 sig figs. So what we need to do here is cut this down to 4 sig figs, in which that means everything past number 9 here would be irrelevant to us, in which that would just be 0. So our final answer would be 32,509 or 590.00, but these zeros are actually irrelevant. So it would just be 32,590. And now let's take a look at B. B is dealing with some addition here. So first let's take a look at the sig fig situation, or least numbers after a decimal situation. Or actually let's first calculate it. So we have 5.1125 plus 0.67 plus 3.2, and that would give us an answer of 8.9825. but we want our answer to have the least numbers after a decimal point of one of the least numbered point, or number rather. So this one has 4 numbers after a decimal point, this one has 2, and then this one has 1. So this is the number with the least numbers after a decimal point. So we want our answer to only have 1 number after a decimal point. Decimal points right here, so the only number that should be staying here is 9. Everything past your 825 goes away. We don't need that. So our answer would be 8.9. That would be our final answer. And now let's take a look at C. So C is subtraction. We're going to use the same exact rule here. Let's first do some of the subtraction. So it's going to be 7.662 minus 7.425. And we're going to get an answer of 0.237. But let's first see how many decimal or numbers are after a decimal point. So we have 3, and here we also have 3. So that means our answer must have 3 numbers after a decimal point, as both of the numbers have 3 numbers after a decimal point, in which our original answer actually had 3 numbers after a decimal point. So we could just keep it like this. So there will be some scenarios in which you don't need to cut out some numbers, so we can just leave it at 0.237. And now last one, D, is going to be division. So we have 16.5 divided by 3.45. And we get an answer of 4.78260. And there's some other numbers after that, but we're not going to need that. So here we're dividing. So we need to make our answer the same number of sig figs as the smallest sig fig number. So this number has 3 sig figs, and this number also has 3 sig figs. So 3 is going to be our smallest sig fig number. So we have to make our answer only 3 sig figs. So we have 4, 7, 8 here. Those are going to be our sig figs here. Everything after 2, 6, and 0 are going to be insignificant. So our final answer would be 4.78 with 3 sig figs. Alright, so that was basically it for units, sig figs, and basic SI units. So some big takeaways are the conversions between units, as well as knowing the basic and most universal SI units, and how to depict sig fig numbers or sig figs within a number, whether it be a huge whole number or a smaller decimal point. The rule I go by is the number of sig figs in a number will always be the amount of numbers you use when you put in scientific notation. And also the rules in between dividing and multiplying significant figures, as well as adding and subtracting them. So that's basically it.